get to do that. I have a couple of small things to show you on particles, but I'm going to defer that until later in the week because we have a lot to do with physics today. And so I'm going to start sharing screen here. Clean this up. So physics is a big part of the Unity game engine. And it's a lot of what makes working with Unity really fun because we don't have to handle the physics ourselves. But it's a complex system with lots of properties, lots of things that have to be set. Supposedly, Unity uses PhysX, which is an NVIDIA product. So I've heard that it behaves best on GPUs that are NVIDIA GPUs. I don't have one, so I don't know if that's true or not. So when we look at the physics system, there are three major components to it. There's the rigid body, which is a non-deforming object that responds to forces, collisions, and joints. And by non-deforming, I mean it doesn't change shape. Things don't change their shape. We have the colliders that are invisible surfaces that are used to detect and respond to collisions. And they are invisible. They're just geometry. I'll show you examples of them in a little while. And then the other component is joints. Joints constrain the behavior of a rigid body along an axis. If you're a Maya person, you might be familiar with the term dynamic constraints. An example of a joint is a hinge joint that makes something swing on an axis like a door. So it's constrained to move around that axis. And these are all components that you can add to any game object, and it becomes part of the physics system. Colliders, we'll see, have physic materials. There's no S there, it's just a physic material. And a physic material is kind of like a prefab. It's a definition of the physical properties that are stored in a modular fashion. And what these properties define is how any two colliders react in a collision. It has no effect on it while it's all alone, but when two things bump into each other, this is when the physic materials come into play. And both objects have physic materials. If you modify the physic material in the project view, it'll modify the physic material on any object that has that material. The properties of a physic material include the friction, both dynamic, which is the sliding friction while things are moving relative to each other. They're in contact but sliding. And static friction when two objects are touching but not moving. And the static friction measures how much force it takes to get it going. And the other property, of course, is the bounciness, which is how much of the incoming velocity is returned when the thing bounces off an object. And these properties are combined between the two objects that come in contact. And we can choose to average their properties. We can choose the minimum of the two properties. We can choose the maximum of the two properties, or we can multiply the two properties together. These properties all go from like 0 to 1. And so we can average, minimum, maximum, and multiply. I believe with that bouncy that I set up, I set maximum. And when we're talking about physics, we're also talking about forces. And in physics, forces do work when they are applied over a distance, and this work changes the energy of an object. We talk about forces in F equals ma, force equals mass times acceleration. Acceleration is the rate of change of the velocity, and our energy is 1/2 mv squared. And we have two different types of forces in unity. We have linear forces. These are forces in the X, Y, or Z directions, either global or local. And we have angular forces, or torques, that produce rotation about a particular axis, about an X, Y, or Z global axis or local axis. So linear and angular forces, linear are called forces, angular are called torques. There's also cloth, which I won't do anything with. It's not terribly useful. We may look at it later. So all of these things are components, although we'll see forces often appear as a parameter in many of the other components. Now, I'll warn you, physics affects performance and is fairly expensive computationally. All of this physics requires that we do various numerical methods underneath the hood and calculate when things overlap and blah, blah, blah. So physics affects performance, and how well we model the physics also affects how many cycles we end up throwing at it. And there's some trade-offs that we can make. Another thing to be aware of is that scale matters. In unity, a unit of length, one, like our little 1 by 1 by 1 cube, is a meter by meter, is a 1 by 1 by 1 meter cube. And the reason we know this is because the default gravity in physics, and I can bring up the physics settings here, the project settings, physics, and I see that gravity is minus 9.81, and that's the value of gravity on the Earth in the MKS system, meter kilograms seconds. So we know that a unit of length is 1 meter. You could change that gravity to minus 32 feet per second squared, and then your unit of length would be 1 foot. Our characters are typically 2 meters tall, about 6 feet. So in this, in the project settings here for physics, there are a number of different settings, one of which is the gravity that I just mentioned. And notice we have X and Z slots for gravity, so we can make the gravity point different directions if we want to. There's a default physics material. You could put in bouncy as your default physics material, and then everything would automatically be a bouncy material unless you overrode it by putting a different physics material in your collider. Liba, hush. Sorry, that's my dog. And there's this thing called a bounce threshold. Liba, hey. Sorry. There's this thing called a bounce threshold. And below this threshold, objects won't bounce. And I can show you kind of an example of this in a little Newton's world here. I have these different cubes, that one of which has a projectile script on it that's going to send it off at a speed of 10 meters per second. And so if I play this thing, these little cubes will bounce back and forth. And they're conserving momentum and all kinds of other physics stuff that's going on here. This is, I call this a Newton's because this is an emulation of a Newton's cradle, one of those things with balls that bounce back and forth. In the physics settings there, you notice that the bounce threshold is 2. So any velocity of 2, any relative velocity of 2 or less will not bounce. And so if I set my speed here of my little projectile, instead of 10, I set it to 2, and now I let this play. Instead of bouncing, the objects stick. And it's still conserving momentum. These things are not bouncing, and so they kind of stick to each other. If I set this up to 2.01, just a little bit greater than that bounce threshold, I believe now they will bounce properly. And they do. So that's the bounce threshold in the physics setting too. And if you set this too low, you can get what's called jitter, where objects will kind of get stuck amongst each other and jitter around. There's also something called the sleep threshold. And one of the things Unity does to save on cycles is when a physics object, a rigid body stops moving, it puts it to sleep, which means that it's not taking up cycles. It's gone to sleep. It's no longer calculated. If something bumps into it, it'll wake back up again. But once it's asleep, it's no longer consuming cycles. There's also things like the default contact offset. This is how much things have to penetrate each other before they generate a collision. And its default value of 0.01 is okay. There's the solver iteration count. This is how many cycles of numerical method iterations is thrown at a particular calculation. The default here is 6. You can set this up to a higher number and it will do a better job of modeling the physics, but 6 works pretty well. The query hit trigger has to do with whether ray casts, which we'll see later, intersect with trigger colliders. And there's adaptive force, which is a little more computationally expensive, but if you have a big pile of rigid body objects that are tumbling over each other, adaptive force can make them behave more realistically. It does cost cycles. And another one is the layer collision matrix. And you remember we have all these different layers. The default layer, transparent FX, ignore raycast, water, and UI. These are the default layers, but we added our own custom ignore layer, for instance. And this collision matrix shows who collides with whom. If you turn off one of these check marks, the transparent FX will no longer collide with the ignore raycast objects. So this will turn off collisions between different layers of objects. So that's the physics settings. These are the project settings, physics, and there's a whole raft of them for 2D as well if you happen to be working in 2D. But these are the physics settings. There's some other ones that deal with how contacts are generated, how things interact with different places in the world, how the friction is developed, what kind of numerical method solver is used. In general, the defaults are fine, but you can fiddle with them if you want to. So that's the project settings. Now, rigid bodies. As I mentioned, a rigid body is a non-deforming object that responds to forces and collisions. And it doesn't deform. A sphere is always a sphere, and this makes collision calculations simpler. For a rigid body to work, it needs a collider component. For instance, if we have a little scene here, don't save. If we have a little scene here and I have this little ball and I turn off its collider and I play this thing, you'll see that the object falls, but it just goes right through the terrain. It doesn't interact with other objects because it doesn't have a collider. So in order for a rigid body to interact with other objects in the world, it has to have a collider. It has to have a mesh filter and renderer if we want to see the object. And the collider has a slot for a physics material. It's the default physics material that's in the project settings, but we can override it by inserting our own in the collider. I've got this little object here. It's got it has a rigid body on it. It has a mass. It has drag. This is kind of air friction in the air. It has angular drag. That's how much friction it has to rotation. And it has gravity. And because it has gravity, this object falls and rolls around the world realistically. This other little cube here didn't fall, and it's a rigid body, but I have the gravity toggle turned off in it. So if I push this thing, it moves, whoops. Let me start this scene again. Let that get out of the way. I'll push this and it goes off. It's responding to physics. It's bumping into things, but that little cube's use gravity toggle is turned off. And so it's just floating around, bumping into objects without any gravity. So objects, rigid bodies have mass. They have drag, which is the air resistance. They have the angular drag, which is resistance to rotation. And they have this toggle whether they use gravity or not. Now, another setting is kinematic. And is kinematic is set when we're going to control the behavior of the rigid body ourselves. When we're going to do it either with a keyframe animation or if we're going to control its position with scripting. And it still behaves like a rigid body. It still interacts with other rigid bodies and bumps into them and collides with them. But with the is kinematic checked, it doesn't move on its own responding to physics. And so in that little Newton scene, one of the end cubes here is set to be is kinematic. And that means it doesn't move. It would move if I scripted it to move or I put an animation on it. And I've done this with the two end cubes. Both of them are is kinematic, whereas the cubes in between are not is kinematic. They're going to move relative to forces and collisions. We can set up a little cube that has an animation on it. Here I have an animator with an animation on it that's going to drive this thing forward. And let me show you a little trick here. If I focus on something and do a Shift F, and then I can back up a little bit. If I start this thing off in pause mode and play it, I can now step along. Whoops, it didn't work. I want to Shift F this thing. Shift F. Whoops. Shift F. And now when I step along, it's not working. Damn. Well, anyway, it's animated and it flies off along and hits the object, and it stopped because that's where its animation ends. So this thing went ahead and hit this. There's some little glitch going on here with this thing. If I do this without pausing it there at the beginning, it penetrates the object. There's something wrong with my system right now, and I can't figure out what it is. But if I pause it for a little bit and let the animation kind of catch up, and then unpause it, it properly hits the thing. Well, it didn't that time either. So there's something going on here that I'm not sure of. So is kinematic is checked if we want the object to be a rigid body and collide with things, but we don't want it to move, or we're going to control it with an animation or a script. The other settings, well, there's interpolate. This is something you can specify that it either interpolates or extrapolates. This throws extra cycles at the behavior of a rigid body, but it can sometimes smooth out motion. Another thing is constraints. We can freeze the position in X, Y, or Z of an object, and it won't move then in that specific direction. And we can also freeze rotation about different axes. And I use that in the Newton scene here. Each of these little cubes are free to move in the X direction, but they're frozen in Y and Z, and they're not allowed to rotate at all. So that constrains these things to move back and forth only in the X direction here. So those are constraints that we can apply to each individual rigid body. So there's also collision detections, and this again is another performance hit. Discrete collisions is the default, but if we have very fast moving objects like bullets, these things can penetrate an object and get through it before they actually collide with it. And so they penetrate walls. And so this is something that we put on very fast objects, continuous dynamic, and on the targets we put continuous. And this improves the way collisions are handled. Here's another little scene with, whoops. Here's another little scene with a little projectile that has a script on it that gives it a speed. This is the same script I used in that Newton's cradle. So this is going to give the object a specific speed of 20 meters per second. And it does it in its awake function where it says get component rigid body velocity, and it assigns it to a vector in the X direction multiplied by this public variable speed, which is 1 by default, but in my in my scene here, I've set it to be, where is it? 20. So this thing's going to take off at a speed of 20. And I want to try and do that same thing again here, where I shift F and focus on that object. And now I want to step through this, and I'm hoping that the scene view will follow that properly. It's not. Why is it not doing that? Shift F is supposed to make these things follow, but it's not. Well, anyway, as I move it along here, I've got the pause on and I'm stepping it. And now I want to look at this kind of from the side here as it comes in and collides with the cube. So as I'm stepping along here, it penetrates. So you can see these colliders are now overlapping. And here's where the collision physics goes on. It figures out what the change in momentum has to be. It gives that other cube a velocity, and then the two things kind of fall and bounce away from each other and take off. Now, I mentioned that rigid bodies have mass. So if I take this projectile and I make it 0.1 kilogram instead of 1 kilogram, it now behaves completely differently. Now when it hits it, instead of knocking the thing over, because it's this little lightweight thing, it just bounces off it. If I make it heavier, it'll have a much bigger effect on the cube that it hits. If I make this, say, 5 kilograms, it's now a heavy projectile, and it'll send that red cube that it hits flying when it hits the thing. It sends it off into the ozone because it was much more massive. And so the mass matters in the relative behavior of two collisions. Later, when we get to scripting, we'll talk about the update function that happens every cycle or every frame. And we'll talk about the fixed update function that happens every physics time step. Physics goes on at regular time steps, by default 0.02 seconds. This is something you can change in the physics settings or in the project settings for time. But the default is 2/100ths of a second. And we'll deal with that later when we get to scripting of physics objects. Now, as I mentioned, we have forces in Unity. And here's a little object. There's a little sphere, and I have on this a component, the constant force component. This component applies a force constantly to the object. Now, if I just run this, the thing will fall and bounce around on the world. But if I apply a force, say in the negative X direction, this is going to push it in the world's negative X direction, which I believe is to the left here. So that force of -1 is pushing the thing to the side, and it's pushing it constantly in that direction. It runs up against the hill and it can't climb it because I'm not giving it enough force to get up that hill. If I give it a bigger force, -10, it will drive it right up the hill, I'm sure. And away it goes with a constant force. in the X direction. Notice if I give it a vertical force of 9.81, that'll exactly balance gravity, in which case now it's just going to kind of float. And this is the same as if I turned gravity off. I can still push the thing around, but it behaves just like that object that had gravity turned off. Now that's force in the world, in the X, Y, and Z coordinates of the world. But I can also give it a relative force. And this is going to be with respect to the object's axes. And right now the object is aligned with the world. There's the X, Y, and the Z axis is off in some other direction. So now if I give this a -2 force, this is going to initially push it along its local x-axis. But because the object is going to rotate, that axis is going to point different directions. And so the force is going to push it kind of randomly around in different directions. It's pushing it along the x-axis of that object. And so we have the thing kind of bouncing around sort of randomly. So that's a relative force relative to the object's axis. This is the kind of thing we might use with a rocket. We have its forward direction and we want to push it forward. And so we would apply the force in the object's Z direction, which is its forward direction. Torques apply rotations about particular axes. And so here's my X, Y, and the Z axis is off in that direction. So if I apply a torque of, say, 2 about the Z axis, that's the axis that's pointing into the screen here, this is going to roll my object about that axis, and the thing is going to take off in one direction or another. It's rolling around the Z-axis of the world, around the Z-axis of the world. So it's always going to rotate things about that axis. And of course, the relative torque is exactly the same thing, but with respect to the object's axes, which are going to be changing all the time as the thing rolls around. So again, we'll get some kind of weird behavior here as it rolls around the different axes, but it's constantly trying to spin it around that blue axis. And so we're getting strange behavior. And again, this is something that you might do with a rocket that you want to spin around its forward direction to make it a spinning rocket. So that's forces. We have linear forces in the X, Y, and Z, either world or local axes, and we have torques, again, either about the X, Y, and Z world axes or the object's axes. I'm going to pause here and entertain questions. Anybody got any questions? That was a lot of material presented fairly fast, but we have a lot to cover in physics. Okay, no questions? Back to sharing screen. So all of this has been using colliders. Colliders are invisible surfaces for collision calculations. And they come in 3 different flavors. There's the primitive collider, which is either a sphere, a box, or a capsule. And these are the simplest and fastest colliders because the shape is defined by a formula. A sphere only has a center and a radius, and the whole surface is defined by a formula. A box is a rectangle, and it only has length, width, and height. And a capsule is kind of well, I'll show you a capsule in a minute. It's got round ends and a cylinder in between. And the mesh is the collider of some complex object. And the wheel collider is a very cool one that we'll use to make cars. And I'll show you that much later. Colliders have properties. One, they have a physic material. The collider is what the collider's physic material is, determines how that object interacts with another collider. And there's also a setting for is trigger. Is trigger is used a lot in scripting, because if the is trigger is set, then objects don't collide with it, but they send messages to scripts when something penetrates its collider surface. So an is trigger collider is not something that you are going to push around, but it's going to send messages that we can catch in scripts and do some kind of behavior. For instance, you'd put an is trigger on a bullet, and when it penetrates your player, that's going to send some message to a script that is going to then deduct points from your player. So let's see, collider. Don't say. So here I've got a bunch of different objects. I've got this beam object, and its mesh filter is a cube, which means it looks like a cube. It's got length, it's got X, Y, and Z scales, but I've put a capsule collider on it. So the collider does not necessarily need to match the geometry of the object. And if I put this in wireframe so that I can see that collider, you can see now that the beam, which is a rectangular box, you can barely see it, but its collider is a capsule. It's this cylinder with rounded ends. And so when I play this thing, while it looks kind of like a box, is rolling around the world like a cylinder, like a capsule that has round ends and a cylinder in between here. Over here is an actual capsule that has kind of a matching collider. And somewhere here is a little sphere that I've put a box collider on. So instead of it rolling around the scene, it behaves as though it were a little box. So the sphere has a little box collider on it. The capsule has a proper capsule collider on it. And the beam, which is a little box, has this capsule on it. So these primitive colliders, the box has a center, X, Y, and Z, and this center is relative to the object that it's on. So usually this is set to be 0, 0, 0, and it has a size. So we can make it bigger or smaller than our object, and you can offset the collider by moving its center. The sphere also has a center, again, usually at 0, 0, 0, and its size is determined by its radius, what the radius of the sphere is. And the capsule has I think it has a center as well, but it also has the width of the capsule and the height of the capsule, and whether the capsule's direction is in the X, Y, or Z axis. Now, somewhere in the documentation, it says, avoid having more than one collider in an object. I find this not to be true. You can have many colliders in an object, especially if one of them is a trigger, because that then sends messages to a different script. So those are the primitive colliders, box, sphere, and capsule. And as I showed you, they can be mixed up and done all kinds of weird things with. Primitives are usually good enough, much more efficient than mesh colliders. Mesh colliders are a bit tricky. Here's a mesh collider. Here's my little lerps. And the mesh colliders are these kind of little blue things. And there are a bunch of little triangles. And if I were to shoot a bullet at lerps and it hit his mesh collider, it would trigger the various messages and so forth. But mesh colliders, because they're so complicated, do not interact with other mesh colliders. And so if I play this, what I'm going to find is that my little lerps character just falls through the geometry. And that's because the terrains are mesh colliders. So they're a special kind of mesh collider. And the lerps is a mesh collider. And so they don't interact. And in fact, if we look in the console here, I got this error message when I ran that scene that says a non-convex mesh collider with a non-kinematic, that means the is kinematic is not checked, is no longer supported since Unity 5. If you want to use a non-convex mesh, either make the rigid body kinematic, that is, set the is kinematic feature on it, in which case it won't move unless you move it with an animation or a script, or set its collider to be is kinematic. So if I go over here and I go to its mesh collider down here, here's the convex setting. And if I press this, you notice that I now have a collider around this little lerps object. And it's a convex collider. Convex, if you think about shrink wrapping something, you take the shape and you shrink it down so that it covers everything. And a convex collider has no indentations. It has no valleys in it. It's all peaks. And so this shrink-wrapped collider is wrapped around the mesh, and now it behaves properly in the world, and it stands properly on the terrain, and I can go over and knock it down, and it bounces around properly with its little bouncy material. And that's because I have set the collider to be convex. If unchecked, it does not interact with other mesh colliders, especially terrains. The convex collider is limited to 255 triangles. So if it's a really big, complex object, sometimes this won't work. And often this makes colliders that are inconvenient. Let me do something funny here with my lerps character. Let me scale it up and make it really big. So I'm going to make it 10 times bigger, 10 times bigger, and 10 times bigger. So I've scaled this character up. And remember, its collider is this convex thing that doesn't allow for any embayments in it. And so if I try and run in between lerps's legs here, in between this arch, I end up hitting the collider and knocking lerps over And because he's big and tall, he falls a lot differently, but he bounces around and behaves properly. But because his collider doesn't really match his shape that well, I can't really interact with individual parts of him because I'm running into those convex colliders that extend all over the place there. And so often with this kind of setting where we want to have an arch or we have some doorway structure that we want to be able to walk through, but its convex collider closes the opening, we'll generate what we might call compound colliders that approximate the object's shape. And so let me go to this next scene here, where I have a compound collider. Don't save. And so now here's my LURPS. And I've turned off the mesh collider, and I've added a whole bunch of shapes. I've got an arm that is a cylinder. I have the mesh renderer turned off. I can turn it on and off, but I've turned it off so that I can't see it. And I've got another arm over here that's a cylinder, and I've got a sphere for the head, and I've got a box for the jetpack, and I have a box for the legs, and a box for the other leg, and a capsule for the torso. So I've made this compound collider out of a whole bunch of children objects, all of them with their mesh renderers turned off so that I don't see them. And now with this proper collider, I can now walk through the arch without knocking the character over. I can still, of course, run into his feet and knock him over. And now because now I can actually walk up under his arm because I don't encounter that capsule collider. And so I can interact more realistically with this object. I could even walk under him there without colliding. So that's a compound collider. And we use that to approximate mesh objects whose convex collider closes the archway that we want to be able to walk through. An example, an object with legs and a crossbeam that we want to be able to walk under, or my character that I've got there. So some warnings about colliders. Colliders interact with each other differently depending on how their rigid bodies are configured. And leave a hush. There's three important configurations. They're static colliders, colliders that don't have rigid bodies. They're rigid body colliders that are fully controlled by the physics, and they're collisions where one of the objects is kinematic, and it's controlled by animations or scripting. And I'll pick that up next time when I continue talking about colliders, joints, and other physics systems. So I'm going to stop sharing here and entertain questions from the world. That was a lot presented fast, but physics is really cool. Remind anybody who hasn't typed their name in chat to please do so.
Thank you.
Thank you. I'm going to stop recording.